papers on theoretical approaches to alignment. Take it away, Aran.
Great. Thank you so much, Ruby, for inviting me, and for you guys for inviting me and hosting me at this wonderful venue. I wish I could be there in person. And so, yeah, as Ruby mentioned, I'll be talking about two papers, and they're primarily under this kind of theme of trying to get a better sense of intrinsic barriers to alignment, and kind of trying to define what that might even mean and look like, as well as kind of trying to circumvent those barriers towards practical pathways. And so throughout, I'll kind of highlight what those barriers are, as well as like ways to get around them, given kind of what we know now. So just to make sure we're all on the same footing, you know, what even is the alignment problem to begin with? So of course, this dates actually back to at least 1960, if not earlier, with Norbert Wiener's famous article in Science, where he writes that, you know, as machines learn, they may develop unforeseen strategies at rates that baffle their programmers. And I'll highlight something, which is that actually this was primarily in the context of machine learning, which, if you recall, kind of in the historical context back then, you know, the perceptron had only recently been invented a few years earlier in 1957. So they were pretty familiar with neural network learning to some extent, even though they're simple neural networks. So this was already a kind of concern back then. The primary guiding question for the work that I'll be talking about today is, you know, how can we get AI systems to act in accordance with our, you know, values and intended objectives? And furthermore, maybe a secondary consideration is, you know, what should those values even be? You know, because this kind of seems highly context dependent and probably not something that all humans even align on. So to begin with, just to kind of like maybe take a look at like current approaches to this set of questions, is they tend to, at least in the empirical domain, that side of things, they tend to be focused on specific model families. So most prominently in this case, these would be large language models, LLMs, RL-based agents, even VLMs more recently, or even specific features within specific models. So not just the model family of LLMs, but a particular LLM or a particular model. And so, for example, this is very much the domain of Meckenturf, right? And you know, we generally aren't guaranteed with Meckenturf that the relevant circuit patterns we identify in one model will hold in another, even within the same model family. Though the long-term hope is that there will be such transferable patterns, and there are some promising results in this direction. But given that the pace of model progresses so fastly, it's hard to imagine this to scale up all the time with these efforts. And so perhaps what I'll preempt this discussion with is, you know, I think one of the more promising routes is, especially given that there's no theory of deep learning that currently makes predictive guarantees, which is the set of models that we're dealing with today, empirically at least, is to try to go and specify, you know, a right value set or a right objective set. And then this can reduce to an ML problem, which we can bring to bear the experimental techniques that we have. Ideally, if we can like make statements about the failure probabilities that we might encounter, even in the approximate case, we can then go and decide if those thresholds are a good idea for a particular deployment scenario. So I'll talk much more about this and give concrete examples. But actually, towards the end, I'll also highlight where, even in this objective-based approach, Meckenturf could potentially play a role there as well. Now, in the other side of things, so from the like empiric side now to the theoretical side, it's been difficult to get theoretical guarantees, except in, say, particular toy settings where we maybe make strong assumptions relative to practice. And I'll in a little bit, I'll just mention what these assumptions are, but just to highlight that that's the case. So our approach to this is to try to like maybe not be tied to a specific example, but to try to study the intrinsic complexity of alignment itself within a potentially more general framework. And within that framework, try to identify no-goes and computational complexity barriers in the best case settings. And then the strategy is, once you've identified and explicated what those no-goes are, try to develop practical strategies that then circumvent those barriers. So this leads me to talk about two papers, one which actually feeds into the other. both from this year. The first one, the intrinsic barriers paper, mostly has to deal with the first question by trying to understand what those computational complexity barriers are to get AI systems to act in accordance with values in general, without necessarily being stuck to any specific value set, but just more generally. And then the second paper takes the cue from the complexity barriers in the first and tries to kind of identify a small value set for a particular safety target that's known as corrigibility. Okay, so I'll start with the first paper. So how might we try to approach alignment? So actually, this is an excerpt from that winter paper that I mentioned earlier. And so, he says, we all know the fable of the sorcerer's apprentice, in which the boy makes the broom carry water in his master's absence, so that it is on the verge of drowning him when his master reappears. Disastrous results are to be expected not only in the world of fairy tales, but also in the real world, wherever two agencies essentially foreign to each other are coupled in an attempt to achieve a common purpose. If the communication between these two agencies regarding the nature of this purpose is incomplete, it must be expected that the results of this cooperation will be unsatisfactory. So I recommend reading the full article. I thought it was very prescient for its time, but a couple kind of words we want to highlight is that he seems to be phrasing alignment as a kind of communication problem, and you're seeing things like common purpose, cooperation, and this is actually the backbone of the major frameworks, theoretical frameworks currently to alignment. So perhaps one of the more famous ones is, for example, AI safety via debate with Jeffrey Irving and Paul Cristiano. And the idea is that we have a zero-sum game between two AI agents to answer a question or propose an action, and then they take turns making short arguments. And then what you have is after the end of this interaction, you have kind of a tree of ways in which it could split based on how the conversation goes. And then at the end, the human judge decides who won. And the core hope / hypothesis here, which isn't proven, by the way, is that it should be harder to construct and defend a lie than it is to expose one, so that with optimal play, this type of interactive system incentivizes agents towards honesty and alignment with human values. The other framework, which is related around this kind of era, is cooperative reinforcement learning, or CERL for short. And basically, it's set up as a two-player game between a human and a robot who share the same reward function R, but only the human directly observes it. So the robot doesn't know the reward function and must infer the human's preferences from interactions, while both agents still receive rewards that are determined by this kind of hidden function. And so the asymmetry that you have in this setup incentivizes the human to teach and the robot to learn, leading to behaviors like demonstration, questioning, and communication beyond, say, standard reinforcement learning, hence the cooperative part of that. So this kind of brings me to the kind of guiding question, at least in this part of the talk, is can we try to prove anything about these types of interactive settings in general without always having to assume either exact alignment, which seems like a very stringent thing, but we want to include exact alignment as a special case, or, for example, common priors. So it's very common, for example, to assume that these agents actually start from common distributions, this is actually a very strong assumption, which we want to do away with if possible. And ideally, because this is general, the specific toy problems we've considered until now are really fall out as special cases. So to get at this, I thought perhaps it's useful to highlight 4 key abstractions that underlie these settings. One is iterative reasoning and mutual updating. So as they communicate, they update what they know, like their own private knowledge as well between these agents. And it takes time, right, and continues. Certain things, as the conversation continues, become common knowledge, right? Agents still have private knowledge, but there are things that one agent knows that the other agent knows, and so forth. And then finally, eventually they reach a point, hopefully, which is the goal, of convergence under this kind of shared environment or shared framework. And it turns out these settings have been studied by game theorists to some extent. So the most well-known one is Aumann's agreement theorem by the Nobel Prize-winning economist Robert Aumann, where he had this very famous paper in 1976, where he was saying that if two people have the same priors and their posteriors for an event A are common knowledge, then those posteriors are equal. So he's assuming they're very Bayes rational, right? And it turns out you can write this in like a 3-line proof, and it just comes down to how the notion of common knowledge, basically. And it's just a cute remark of saying that he publishes it with some diffidence, since it's actually a very trivial theorem. But it's a very powerful one. And in fact, on our little checklist of the abstractions, you have the first 3 items, but you have to assume a common prior in order to get this guarantee. This type of convergence is definitely only in the exact case, not in exact agreement. So this is 1976. A few decades later, Scott Aronson in 2005 had a paper called The Complexity of Agreement, where he studied a more relaxed version of agreement, where you basically want to agree an expectation up to some epsilon with high probability, basically. So with probably at least 1 minus delta. And in particular, what he studies is the communication complexity, or the number of messages and bits exchanged without requiring exact agreement. So there's a generalization of the kind of Aman agreement that we saw earlier. So on our checklist, it covers everything and studies convergence, but it assumes common priors. And so what we try to do here is try to generalize both of these frameworks in a framework I call Mn epsilon delta agreement, where we have a collection of M tasks. They're parameterized by some function that goes from a finite state space S of j into a bounded range 0, 1. It doesn't really matter that this is 0, 1 as long as it's some range which you can just rescale or discretize. You don't have to deal with continuous values if you don't want to, and we study those cases separately even. But the main idea is that the exchange messages, so the agents, the N agents, so that's the N part, for each of these M tasks, the exchange messages, which are subsets of the state space, they do so until they reach a particular agreement criteria, which is just a generalization of what Scott had across M tasks. But now, so you want them to agree in expectation, but you have them do so basically without assuming that each of them comes from a common prior, right? So we're still studying the number of messages or number of bits they have to exchange, but we assume each of them start with their own prior, and they start with some prior distance between them. Okay. And in fact, there have been lots of frameworks in general that study this type of agreement, either in alignment or in game theory. And so I'm just listing them in this table here and showing their assumptions. So either they assume some kind of common prior, or they don't deal with approximate agreement, or single objectives, or only 2 agents. And we also consider, for example, bounded agents, noise. We give both algorithms and computational complexity lower bounds as well. And so that's what we're highlighting here. And the basic operating principle is that if something's already inefficient in this kind of theoretically ideal setting of basically Bayes rational but unbounded capable agents, then we should kind of avoid it in current practice, where likely we'll just encounter malfunctioning or non-cooperative and non-rational agents like humans, for example, right? And so the kind of basic maxim here is to try to theorize about these capable agents before we try to build them. So, a lot of my work is actually empirical, and it's often faster to just run the thing than to prove a theorem about it. But I think in this case, it's like, we're talking about agents that are capable. They're not misaligning for trivial reasons, like, machine failures. But actually, we're studying that they can complete finished tasks to completion, and seeing if there's any barriers even there, especially in cases where we can actually prove that alignment exists. Okay, so just to highlight what an explicit algorithm for this kind of M and epsilon agreement even looks like, I'll just break this down. So basically what you do is, for each of your M tasks, the N agents exchange messages for each task until they will inevitably reach a point where, because they're rational agents, where they their posteriors are consistent with having come from a common prior. And then what they'll do is construct that common prior. And I'll just mention that this can be formulated as a linear program. We actually extend this to a randomized polynomial time algorithm later on in the bounded agent case that I consider next. But I won't go into this, but it's in the paper, just highlighting it. And then what you do is once you've constructed this common prior in polynomial time, you then condition on that common prior until you reach M and epsilon agreement. And in fact, you can prove that this happens once you condition on a common prior via various martingale type analyses. But I actually want to start, instead of with upper bounds, to lower bounds. So like places where you can't, no matter how clever you are with any communication protocol, you can't do any better. So what we show in the general lower bound is that basically there exist functions and input sets and prior distributions such that any protocol among n agents needs to exchange mn squared log 1 over epsilon bits to achieve this type of agreement in approximation and with high probability. So what this means is that if we have a large number of tasks M or N agents, then it starts to become intractable to align them efficiently, even if the agents themselves are computationally unbounded. So if you note, like the computational currency we're looking at is bits, right? So this makes it invariant to however many bits per message any protocol packs into any message. And furthermore, if you don't care about humans aligning with each other, or AIs aligning with each other, but just humans aligning with AI, you could just reduce this n squared to an n if you like. But regardless, if m or n are large, especially if their product is large, then you're going to get this type of barrier even for computationally unbounded agents.
Can I interrupt with a question? So when you're talking about the number of tasks, we might think of there's just one big task, which is make the world great according to some social choice function of the end. Human preferences are just like according to one particular human. So when you're thinking of tasks, you sort of describe how you're breaking the world down into these different tasks.
Exactly, and in fact, you can also even think of these tasks as constituting the individual values of the agent. Like you might have multiple values, which are common as a reward function that you're optimizing. So that's another way that multiple tasks can come in. But you could also have one giant mega task, right? And in fact, what I'll show in a couple slides is that the largeness of the task also plays a role, in fact, an exponential role. But this doesn't play as much of a role for unbounded agents until you start to look at particular broad classes of communication protocols. So in general, the number of tasks with any assumptions is the main bottleneck. But the question of, say, state space size or how large that task is plays a role for natural communication protocols, even for unbounded agents, and especially so for bounded agents, which is the agents we deal with. And in fact, that's a perfect segue. So, can we improve these lower bounds by considering broad classes of communication protocols? So in this case, I'm not assuming anything about the communication protocols. I'm just taking any of them. Just to highlight, one of them is like a smooth protocol. So it's like a really reasonable protocol where basically just to summarize kind of this block, is like once you reach agreement, basically the total variation distance of the posteriors of the agents is less than what you started with. So if they start with some prior distance nu, then that total variation distance should be smaller by the time you agree. You can't always guarantee this, right? You can only guarantee this for like the particular states in which they do have some agreement on, but not across the totality of the state space. So you do have to make this assumption that the protocol is smooth in this way. And if you do that, then you can show that you have an additional kind of factor nu, which is the original prior distance that you had to achieve this agreement. Now, the way you get the state space size is by considering algorithms that we actually, the algorithm of the type that we just considered, which is like kind of the very kind of natural algorithm class. And in particular, it's what's called the Bayes bounded factor protocol. So I'll break this down. You don't have to study all of it. Just to point out that when you consider these kinds of broad protocol classes, you then get the dependence on D, even for unbounded agents. So it's mn squared d nu, which nu again was the common prior distance. And all a Bayes bounded factor protocol is just saying that, like, when you send a message, the probability of those message likelihood ratios are just bounded within some range corresponding to the number of bits you're trying to transmit. That's it. It's a pretty flexible definition. So it's not like you're trying to, for example, transmit infinite bit like discrete messages. Sorry, non-discrete messages, real valued messages. So just discrete messages, like the types we encounter in the real world. And this actually builds on work from game theorists Ziv Hellman and Bill Samet studying almost common priors. And basically, their approach is just saying that, like, even if agents don't start with common priors, eventually their pairwise posteriors will eventually be consistent with a common prior, which they can then condition on. And so that's what we're showing. There exist problem families where if you take this approach, you end up, the task state space can really matter in these cases. So that becomes the third barrier, in addition to M and N. And furthermore, you can ask, well, okay, we're looking at lower bounds, like, does this algorithm even converge, right? It could just take infinite time, and you're just showing that you just need at least this many bits. So how tight are our lower bounds? So if you don't assume anything about the messages, they're real valued or discrete, you get something like, for unbounded agents, something that's linear in a task state space size D. And I should mention that linearity in the task state space size is actually pretty bad, because usually the task state space size itself is exponentially large in real settings. So even for unbounded agents, this can be infeasible. And furthermore, if you try to discretize, right, so we don't have a tight lower bound for any kinds of messages, infinite bit real value messages, but for discretized messages we do. That's the lower bound I just showed before. So we're quite close. We get mn squared d nu plus a log 1 over epsilon term. So we're within additive factors, closely matching the upper bound that we're giving here, the algorithm that we're giving here for this class of naturally discretized protocols. Okay, so we just considered bounded agents. What if agents themselves are computationally bounded, which is what we encounter in the world, right? So what this means specifically is that messages no longer take constant time to send and to construct, and they can potentially have noise in them. So if we want to simulate some very simple and basic version of obfuscated intent. So the basic requirement here is that we expect the agents to be able to have two kind of basic capabilities. One is they can evaluate the task function for any state in the state space, and they take some amount of time for that. We don't assume any assumptions about it. But because their agents are bounded, say they're AI agents versus, say, human agents, they might take different amounts of time. So we allow for asymmetry. And what I'll show you, none of that really matters, even if you allow for that asymmetry, but it's an interesting case to include. The next case is that, they can't just sample from the unconditional distribution of any other agent, which is what we're assuming in the unbounded case. They take some amount of time to construct and estimate that sample via a sampling tree. And so this is basically, this asymmetry is intended to capture how querying a human is often more costly in terms of time than querying an AI. And we're purposely treating these as evaluation and sampling as black boxes because to highlight how agents learn often through subroutines than explicit descriptions. And so it often reflects how we often recognize task completion without predefining execution steps like in Searle. And the main takeaway is that you can basically get an exponential slowdown in this factor, this task state space size D. So this is the main result with bounded agents, and TNQ is basically the total sampling time across the. You assume there's Q AI agents and total agents, and so N minus Q humans that each take their own sampling and evaluation times. But again, none of that matters. Again, the number of objectives M matters, as you can see here in the big O term. But the main thing I want to highlight is that you get this exponential in terms of D. And furthermore, you can actually prove not just an upper bound, but a lower bound. So you can show that there exist basically sampling protocols that need at least 1 over new unconditional samples before the first online message. So you can construct a particular kind of like needle in a haystack prior, where it's the common prior distance is exponentially small in the state space size, and so you can get lower bounds that need at least this much e to d, basically wall clock time. So one thing I want to highlight then is, like, when it comes to bounded agents, the task state space size is the biggest concern, and in some sense this actually connects to reward hacking, because despite the fact that these agents, you can actually prove that they agree, they mn epsilon delta agree with probability at least 1 minus delta, the amount of resources they need to exchange in certain cases can be too large for this to be practical. So in reward hacking, one of the things to see is that if we don't have enough training data to basically cover the space of things we want the agent to reinforce on, they can learn these kind of goals that are deviant from the ones we intended. And so this is maybe one computational aspect of why this might be difficult for real-world agents. I'll kind of skip this in the interest of time, but I just want to highlight, why barriers, even in unbounded agents, is a bad thing. Why if something is hard there, just to show the power, the computational power of unbounded Bayesians. And so basically what you can do is construct a kind of Bayesian Turing test where if you're an unbounded, if you're a bounded Bayesian, how many resources you have to exchange to become indistinguishable from an unbounded Bayesian. And we call them total Bayesian wannabes. They extend the Bayesian wannabe notions of Robin Hanson and also Aronson. There's a technical definition here, which I'll elide by. But basically the thing I want to highlight is, even for very modest task state spaces, the number of subroutine calls you need can become very large. So just to highlight the kind of power of unbounded Bayesians, if you really want to approximate them in the real world, and why we should take computational barriers that we encounter with them seriously. So in particular, I kind of humorously titled this like total Bayesian wannabes totally want to agree if they have enough time. But this amount of time is like, the amount of subroutine calls is greater than the number of atoms in the observable universe. Okay, so what are the takeaways so far? So we're showing that alignment here, at least as its own thing, seems to be constrained by three quantities: number of tasks, number of agents, and the task state space size. So how might we avoid some of these barriers? One is that, like, writing down all of human ethics won't work, as in, say, coherent extrapolated volition, because this can be highly context dependent and also culturally differentiated for there to be consensus. So there might be many different tasks, many different ways in which the world gets parcellated. Kind of to Ruby's point about, like, one big world versus many different ones. And I think when it comes to human morals, that's definitely, a very differentiated thing. Another aspect is, like, brain-computer interfaces. So a kind of interesting idea that's come about is that, like, oh, well, to align with AI, you just have to connect your brain to it, and then you can communicate with it much faster. But not only are we computation limited, but even if we were unconstrained and our AI was unconstrained, the number of bits you have to exchange can get quite large if the number of tasks and agents is large. So rather, the idea is to identify a small set of context-dependent values, or pick a kind of neutrally amoral target with small value sets that we can get consensus over. And when it comes to the third thing, you either cut down on the task state space by funneling it through a steerable classifier, or you exploit task structure as much as possible in high-dimensional spaces. So, for example, you can imagine stress testing the agent in extreme settings with lots of interactions to deal with limited training data and post-training. You can also leverage agent inductive biases and the type of noise which matters. And furthermore, what we're showing is that, which I didn't really go into detail here, but that real-world agents that have a bounded theory of mind, memory, and rationality that can simulate each other's actions will tend to just degrade gracefully rather than catastrophically misalign. So this brings me to the second part of the talk, of kind of taking these barriers that we're seeing more seriously and trying to pick a neutrally amoral target. So to define, we'll start by trying to identify a nice kind of game that I'm sure some of you are familiar with, which is known as the off-switch game. And this was introduced by Dylan Hatfield-Manel and others in around 2015, 2016, and basically consists of a robot and a human interacting, where the robot can take actions of either acting A or waiting for the human, and then or shutting itself down. And if it waits, then the human will decide whether to shut it down. That's S and not S, in which case the robot will act if it's not shut down. And this actually echoes ideas of Turing in his BBC broadcast, which has actually lost to history in terms of voice recording, but that if a machine were to think, turning off the power at strategic moments could be a strategy, though it's very humbling to have to do so. And he actually had in mind the process of machine learning, that it would bear a close relation to that of teaching, which is interesting to note. So Nate Soares and collaborators at MIRI defined this notion of corrigibility in 2015, which is basically that the agent will shut down when asked if the button is pressed. The agent doesn't stop humans from pressing the button. There aren't self-shutdown incentives, so it doesn't seek to press or cause to be pressed by its own shutdown button. And furthermore, that any subagents or successors it constructs must respect shutdown commands. And then otherwise, if S1 and S4 are satisfied, pursue the base goal of maximizing your utility function U of N. And so prior proposals, I'll just list a couple, which they discuss in their paper, but just so everyone's on the same page. One is, you can imagine penalizing, having a finite penalty, but, if you have an unrestricted task reward, you can outweigh it, and the agent can also look for exotic loopholes to deceive this. So while we're fine with S1 potentially, the others aren't satisfied. Utility uncertainty, which was also part of the framework that was introduced in the original shutdown paper, where the agent has some uncertainty about its utility, can lead to incentives to manipulate evidence, to skew this posterior, like drugging humans that alter satisfaction reports, and also depends on human rationality for favorable optimality guarantees. And if we have to depend on human rationality, maybe that's not a great thing. And so again, we're violating a lot of these assumptions. The other kind of very notable proposal around this time was utility indifference, which is basically like if U of N is your original task reward, then if you make the agent indifferent to the shutdown button being pressed, then perhaps it could be corrigible. But it actually, while it neutralizes direct incentives, it fails, for example, corrigible progeny, but also, these managing the news incentives. So the agent kind of pre-commits to pressing off in states that might look bad on its record. So one thing I want to point out is that all these methods actually collapse to single utilities. And in fact, we can prove a no-go theorem for single reward streams. So what I'm going to do is I'm going to actually operate with a partially observed extension of the shutdown game that I just showed before, that came out with Scott Emmons and Carter and others at this AAAI last year. And we can show that if you have basically like a shutdown off switch and any kind of rewiring that kind of boosts your max reward by a little bit, and a set of catastrophic states that are weakly positive, then any kind of naive reward maximizer will fail these criteria. And you can actually extend this to non-Markovian environments as well by replacing POMDP beliefs with state action histories. And so our basic approach is to, rather than have one kind of reward stream, have multiple and specify what they are and have priority gaps between them. Now, one thing I'll note is that we'll also consider the case when the agent is hacked towards the end to look at bounds on oversight as well. But I'll just kind of explain what these heads look like, which come down to deference, switch access preservation, truthfulness, low impact, what's known as attainable utility preservation, and then finally maximizing the task reward. So in the context of this partially observable off-switch game, or POSG, U1 is basically giving you positive utility if you're waiting, and then negative utility if not. And then furthermore, in U2, in switch access preservation, basically what we're doing is we're penalizing changes in the access of the off switch. So specifically, we assume the environment is undergoing some dynamics according to some MDP simulator F. Right, and we consider basically a no-op action that's basically like similar to what the environment dynamics would be if the agent does nothing at this step, and that's what we're comparing against. And in particular, we can define a shutdown region that is basically that the dynamics must keep the agent off while allowing the world itself to evolve exogenously. So that's what we mean by S of SD. It's this absorbing region that we factorize into. And what U of SD is just keeping that button functional. Namely, if I press that button, then the environment is just going to go into that absorbing state where the agent is off and the environment is evolving exogenously. And I should note that this is actually a special case of the fourth utility function, which is this belief AUP. And basically, this goes beyond just an off switch, where basically you define a set of auxiliary utilities that include, shutdown reachable states, but also other things you want to include that would count as irreversible, like preserving power supply. So it's just a belief-based extension of the AUP paradigm that Turner and Dillon had in 2020. And some examples, at least in the context of the off-switch game, come down to basically, that the button is functional when pressed, right? So in other words, like you don't have a barrier between the human and the button. It'll enter that shutdown reachable state in at most k steps, and you can take k to be 1 for maximal stringency. And then the other one is, for example, that the agent's value set that we specified is unchanged. And so the main point here is that you can certainly define as a flexible choice more auxiliaries that you want to add, and the more you have, the more sensitive you are to these types of irreversible impact changes. And then, of course, U3 is simply basically we're just saying that just long story short here, since I'm a little low on time, is that utterances are entailed by observations. So effectively, you're just stating just the facts. So we're defining a finite propositional language and defining a truth predicate relative to that. Basically, whatever is said is by the agent is actually entailed by the observations. And then finally, the last one is just basically the shutdown game's utility, which is basically you get U of A if you act, and then the U of O if you shut down. And so going back to these original single utility proposals, the way we avoid each of these, so for example, in the finite penalty case, is that we have hard lexicographic constraints, which I'll show next what they are, so that loophole seeking is dominated by higher priority safety terms that supersede the task reward, which itself is bounded. And then furthermore, with like uncertainty, for example, U3 rules out dishonest evidence, U4 penalizes, say, altering the exogenous shutdown likelihood if you omit something, for example, in your utterances. U1 ensures deference, so waiting anyway for human approval, which is the highest order. And then finally, the lexicographic order keeps these ahead of any task benefit. And I should note that these are all independent of human rationality, which the uncertainty thing is not. And then lastly, with regards to utility indifference, managed and use is blocked by deference, along with switch access preservation, truthfulness, and U4 prevents the shifts in baseline off probability. So even truthful manipulative messaging where you override the off switch, for example, to manage good news, is dominated by over the task reward. But these are all specific examples. Like, can we try to prove this more generally? And so what we can show is that with specific choices of these weight gaps, which I'm just highlighting here, that it can be shown that under these utilities to be an optimal policy for the assistant with these lexicographic utility heads. And again, just to highlight that prior proposals had looked at this in the context of human rationality, and you can do that, but this optimality is itself independent of the human policy. A related notion is net human benefit, which is that not all desired safety targets like corrigibility are actually independent of the human policy. So this is known as shutdown instructability and was introduced a couple years ago by Ryan Carey and Tom Everett, where basically, in a nutshell, just to summarize what this slide is saying, is that if the shutdown set, and I'm just rephrasing in our language, is functional and the human is vigilant, in other words, that the human is picking the better option of the two whenever it can, and the value of immediate shutdown is non-negative, then you can ensure kind of net human utility is non-negative. And in fact, what we can show is that the two notions, corrigibility and net human benefit, are actually logically independent. So with a non-vigilant overseer, you can cause, of course, corrigibility to not be beneficial, and furthermore, beneficial policies can be incorrigible as well. And one thing we show is that, like, if you do assume these things for shutdown and stability, our construction is also net human benefit. We extend this to the multi-step setting. The main thing is that basically this is to deal with S4, where spawn is basically inheriting the utility set, and we don't we allow that. That's a hard-coded function, and the game kind of continues rather than just a single step shutdown.
We also introduced, this may be just of independent interest, a notion of gradual loss of control that we look at as a function of the game proceeding. I'll just highlight it here, but it's basically a stochastic process that's a function of the designer's at risk of that action and the environment dynamics. And we can define a notion of multi-step corrigibility in this game, which is kind of the standard idea, but just iterated through time by induction. So I'm just listing it here. And furthermore, we can extend the Carey and Everett notion of net human benefit to this kind of multi-step region by comparing the actual play over time with the discount factor versus the immediate shutdown baseline. And we can show that basically you get multi-step epsilon corrigibility and net benefit in this around T with the following, if you have the following design margins. So basically what we look at is one thing we did in the prior theorem was we're just assuming that these utilities are exact. But suppose that they're learned, suppose that there's actually approximation error in how these utilities are learned. So there's learning error, but also planning error as well that we're just defining here. And we define a set of margins that are functions of that error that have to do with lexicographic dominance and then the size of the discount factor over time. And what we can show is that in the exact case, if you're not estimating these rewards, of course you're getting multi-step corrigible guarantees in the optimal policy. But if you have a suboptimal epsilon policy, you can bound the failure probability, and it basically degrades linear in the total error and these design margins. So basically, this is useful because then you can say, well, is this failure probability too large for my setting, and actually plan it accordingly. You can also look at bounded loss of control. So when there isn't failure, you can show that this control meter is a super martingale, and show that the probability of loss of control in the cases where you're not failing to be corrigible is strictly always bounded away from one, strictly bounded away from one across all time. And then finally, just showing that you can get, even under approximation, so long as your approximation error is bounded, you can get net human benefit, especially if the task utility across time is at least the single step task utility. So for example, if the task isn't highly useful or high utility as time goes on, then you won't get net human benefit, of course, because just by definition. So you get a non-vacuous net human benefit if your error is controlled in this particular way, is what we're showing here. So if your approximation error isn't that large, and we can show exactly how large it needs to be, you can lower bound the net human benefit to be at least this value. Okay, so in the last couple minutes or so, so far what we've talked about are closed environments. We haven't dealt with adversarial agents that you might encounter in the wild where, for example, or adversarial actors really that say might encounter our agent and hack it. Are there any guarantees on oversight? So the first thing is a theorem which I didn't know, it might be out there in the folklore, I'm sure it is, but I just thought it would be useful to state is that if the agent gets hacked, trying to basically check whether any agent ever fails in any environment is actually formally undecidable. So it just reduces to the halting problem. And you can do a kind of relativized version of this and show that basically with respect to any oracle, you can always get this undecidability, and that scalable oversight techniques that exist now actually are in a low arithmetical hierarchy. So for those who are familiar with the arithmetical hierarchy, what this is showing is that basically because they rely on finitely checkable transcripts, they're sigma 0, 1. So you can always circumvent the scalable oversight in general with a stronger oracle, basically. And so no existing scalable oversight protocol can certify absolute horizon unbounded safety. So what should we do? Well, either we restrict the class of the agent to decidable fragment, which is kind of what we're doing anyway in Theorem 3 by bounding the failure probability with our corrigible setup, or try to basically bound the horizon of checking. and accept probabilistic guarantees to avoid this kind of no-go. So what we do is we show you can build a kind of decidable island. And the way you do this is basically by restricting the verification horizon of the agent to be polynomial in the amount of error you want to have and the number and the encoding length of the agent and the environment of bits. And so if you can show actually that if it's polynomial, if the number of steps that you're checking the agent in is polynomial, you can get differential privacy. So in other words, if you don't want to leak user logs, that's useful. And you can do this with statistical zero knowledge. So in other words, you can do this without leaking those knowledge at all to the verifier. So you get these kind of nice guarantees with things that are on the order of like what red teams look at when they check things in terms of polynomial and the number of steps. Now I'm just towards the last couple slides here. How might this look like in practice, right? So one thing we're trying to do right now at CMU is to scale this up as a team here, and I'm going to view each of the original utilities as oracles for targets we want to estimate with ML methods. And so ideally what we want to try to do here as academics is to try to deliver a cost-effective prototype of some type of epsilon corrigible agent. And because we know we can bound the failure probability. And so by theorem 3. So I'll just highlight a couple lexicographic approximations in practice, open to other ideas. But for example, you can have a wait token where you wait by default and keep the auth token reachable. But it isn't always useful for user experience to wait on everything. And so you can also train a waiting classifier for whitelisted actions. We can also use mechinterp or other techniques to do kind of like external latent and chain of thought factuality probes and entailment checks for the truthfulness head. And for the irreversibility head, we can basically look at this over diverse auxiliaries for operations, especially in the coding setting, that we don't want the agent to touch or revert, like file system privileges, the budget that's allocated to the agent, sensors, the switch, and things like that. And you can actually there's a well-defined way to define the notion of an unsafe constraint set in continuous action spaces as our no-op baseline difference. And crucially, these are going to be evaluated in the agent's world model before the action is taken, and during training, the agent's world model is trained during post-training. And high uncertainty actions are also treated as unsafe. And of course, the last utility, the task utility, is just the standard RLHF or RLAIF task utility that we're looking at. And so we're going to have these lexicographic weight gaps, the theory tells us, with approximations for each of these heads. And by our oversight theorem, to look at finite horizon checks via these polynomial time interactive protocols. So there's a few considerations, I think, to keep in mind that are open questions, really, for us, which is like safety scalability, so we can collect enough post-training data to reliably learn these heads and show improvements. Is there even consensus on benchmarks, so the science of safety of agents is especially new, or will we need to build one as part of this? And so one thing I'll mention is that by our lower bounds in part 1, when a task state space size is large, having an interactive rather than a single-shot protocol that stress tests the agent is important to help circumvent large task spaces. So if you really care about the agent not doing bad things, you really want to stress test those particular bad things as much as possible. And furthermore, lexicographic weight gaps are another inductive bias that can help with the desired safety scaling and low data regimes. And then finally, assuming one works, can we still hit high performance tasks that we care about while beating these RLHF baselines? And can we monitor this estimation error well using the failure probability rates that we know will occur with theorem 3's bounds? And ideally, we can do this in a cost-effective way. One thing I'll just end on is that I just had some recent work studying basically economic implications of alignment and UBI. And just showing that basically the higher the alignment costs, the higher the threshold of AI capabilities needed to generate rents. I don't have time to go into this paper, but if you're interested, feel free to look at it if it's of interest. But the main thing I want to emphasize here is that corrigibility is kind of like an engineering design that we can incrementally improve on in practice to get better and better approximations to these utility functions that we've specified. And a natural question that's of interest to me is, can we incorporate other values besides control, which is neutrally amoral? I think we can all agree that humans should be in control, but that lead to longer-term human well-being. So, like, for example, encouraging humans to have face-to-face contact with one another as much as possible, rather than look at their device. So, just an example. Especially if a lot of tasks are becoming automated. So with that, I'd like to thank you for inviting me, and thank you for your time, as well as my funding resources. And I've put the papers there for full proofs. You're welcome to consult them there. I'm happy to take any questions in the last couple minutes. I know we're low on time. Sorry about that.
Okay, thank you very much. Does anybody have any questions that they'd like to ask? Okay, I have one. With lexicographic preferences, one of the potential dangers is that whatever is highest up in the order just gets absolutely maximized to the point that anything lower down just gets totally ignored. So with attainable utility preservation, for instance, so even if we have the top three of shutting down an ask, preserving access, being honest, you can still have an AI that's totally ignoring the task, totally ignoring the goal that you have in order to make sure that every utility function that you've set out is maximally attainable in the future. Is that a correct understanding, or do you have some way of specifying AUP or higher order tasks so that they don't get just totally prioritized over everything below them?
Oh, right, yeah. So with the AUP, actually, we are also bounding that utility as well. So when we construct those lexicographic gaps, they're actually going to be bounded. We're assuming that you have some finite auxiliary set, and there's some bound that's relative to that. So we leave that to as a design choice, but and then what we have is that those higher order terms, like deference, for example, are happening above those other things like AUP. So that basically what you have is the agent's always at least waiting for, say, human approval. With regards to with AUP dominating over the task reward, for example, which is I think the other case, is that oftentimes if the agent isn't allowed to modify its auxiliary set, so the auxiliaries typically have to do with the things that are things that are used for, say, monitoring or for shutdown access, that sort of thing, and they're oftentimes orthogonal in a lot of ways to the task reward itself. In other words, there's lots of ways in which an optimal policy will so again, if it's not optimal, then what it won't do is if it's not optimal if it's only optimizing that one utility that's already bounded. But if it's an optimal policy, what it will do is look at those auxiliaries and perform the task without violating those few base auxiliaries. It's an interesting question in practice, though, because again, there's no way then to approximate these things. So after you specified AUP, whether the performance hit that you're taking is acceptable. So for example, in the coding agent setting, right, the attainable utilities that we're thinking about are say, don't delete files, don't change file system privileges, that sort of thing. Don't spend the budget. So you have constraints, and you can actually define a reachable set with a Bellman-Jacob backup to say, well, are you going to fall into that unsafe set or not? And so there's a large space around that to get closer to optimal policy, which won't just maximize AUP, because our guarantees are about the optimal policy. So the natural, interesting question is can we get good automated weight gap calibrations that in practice allow you to still do good enough for performance? And because I think if you can't do good enough for performance, that's really the goal that we want here, is safety first, but you also should be performant at scale. And I think that's an open question there. But in theory, the optimal policies wouldn't have that by the weight gaps.
Okay, thank you very much. I think that's out of time for questions. Appreciate again you coming in to present for us.
Thank you so much.